Let us see how we can model protein degradation. Let me draw a graph. So horizontal axis is time and the vertical axis is protein concentration. Let us assume that the initial protein concentration is here. And also we assume there is no protein production. The protein concentration level starts decreasing and eventually reaches 0. Everything is degraded. This pattern is called exponential decay or decrease. So this is a typical pattern when protein is degraded inside a cell, when there is no production. When degradation happens, we don't see this pattern or this pattern, but this exponential decrease. Now the question is, how can we model this mathematically? One way of modeling protein degradation is to use a difference equation. So y of I is equal to some parameter p sub y times y I minus 1. So what is this y of I? This is the concentration of Y protein at time I. And why do we care concentration? We will talk about that later. What is this I? I is the discrete time index and it is an integer. You may say I starts from 0 and then becomes 1, 2, 3 and so on. Let's say if in the beginning of your experiment or simulation, your discrete time index is 0. And say after 1 minute, your I is 1. Again, after 1 minute, your I is 2 and so on. And this is your time interval. It can be a second, minute, hour, month, year, and so on. Now I want to talk about this P sub y, which is degradation parameter. And this should be a real number. Also, it is greater than or equal to 0. Protein concentration is always positive. If Py value is negative, then negative times positive, we get negative value here, which is also protein concentration. And this doesn't make sense. So that's why we have this Py always greater than or equal to 0. First, what if this P sub y is equal to 1? What does this mean? This means that y of I is equal to y of I minus 1. This tells us that the Y protein concentration does not change over time. The previous Y protein concentration at I minus 1 is equal to the current protein concentration at time I, which means that Y protein concentration is not changing over time. Now, what if this Py is greater than 1? Let's say we have y of I is equal to 2 times y I minus 1. The equation basically tells us that the current Y protein concentration is 2 times larger than the previous Y protein concentration. In other words, Y protein concentration is increasing over time, and we are not modeling protein degradation here. Now, what if Py is less than 1? Let's say we have y of I is equal to 0.9 y of I minus 1. This equation tells us that the current protein concentration is previous protein concentration multiplied by 0.9. So Y protein concentration is decreasing. Y of I is equal to 0.9 times y I minus 1. Let's say our initial protein concentration y of 0 is 100 micromolar. Then what is this y of 1? Then this is, from this equation, 0.9 times y of 0, which is 0.9 times 100 micromolar, which is 90 micromolar. And how about y of 2? Is 0.9 times y of 1, which is equal to 0.9 times y of 1 is this value, so it's 90 micromolar here. So we get 81 micromolar, and so on, right? Okay, so this is when P sub y is 0.9. Now let's think about a case when this P sub y is 0.1. In this case, we assume that we have the same initial protein concentration, which is 100 micromolar. Y of 1 then becomes 0.1 y of 0, which is 0.1 times 100 micromolar, which is 10 micromolar. And y of 2 is 0.1 times y of 1, which is equal to 0.1 times 10 micromolar, which is 1 micromolar. So you see that when this value, the P sub y, decreases, actually we see more rapid decrease. When P sub y is 0.9, the Y protein concentration changes from 100 to 90 to 81. But in this case, when P sub y is 0.1, the concentration goes from 100 to 10 and 1. It's decreasing much faster.